the way people would try and compensate for excess proppant going into the toe, for excess proppant going into the heel rather, would be to put some extra perforations into the toe, reducing the perforation friction there, making it an easier flow for the proppant to go into the toe, and hopefully evening things up. But what we found was, when we're plotting here, the excess number of perforations, or percentage of perforations in the toe compared with the heel. So if we had what you might call a tapered design with more perforations in the toe, and we put between 30 and 40% extra perforations in the toe clusters, that resulted in a toe bias. We perhaps made it too easy for the proppant to go into the toe. As we reduced that proportion of extra perforations in the toe, our bias reduced until we got that desired 50-50 ratio, when there was between 0 or 1 and 10% extra perforations in the toe. And finally, if we go back to no extra perforations, this is actually a geometric stage design now by definition, and we're back to that heel bias. So probably the important thing to take from this chart is that we do have control over where the proppant goes, just by something as simple as varying the number of perforations in the toe compared with the heel. So it's obviously good news that we can manage where the proppant goes to a certain extent. There are some limitations to heel-toe ratio, and that's why we haven't replaced it, but we've added to it. It still has its uses. The most useful probably is that it identifies these heel-toe trends and quantifies them. You understand the strength of it, 70-30 or a 40-60, and the direction, whether it's a heel bias or a toe bias. What it doesn't do very well is provide us with cluster-to-cluster variability. So if we look at the two example stages on the right, they both have the desired 50-50 split. So they've both got the same amount of perforation erosion going on in the 4 clusters closest to the heel as they have in the toe. But there's a big difference in the cluster-to-cluster variability, and it's not captured in that number. So we need an additional metric, additional way of quantifying this variability. So statistically, there are various measures of variability. Standard deviation and coefficient of variation are commonly used measures. Interestingly, there's no commonly used calculation statistic for human uniformity. It's just calculations of variability that we do. I think we understand they're kind of the opposite, the inverse of each other. But statistically, we calculate variability and not uniformity. So standard deviation is a measure of how far on average each data point is from the average of the data points. So captured in this equation. And standard deviation is typically used when we're trying to understand the variability within one data set, like this. Okay, so the greater the standard deviation, the greater the variability in the data points. In this example, that's the resulting number. However, coefficient of variation is more often used when we want to compare different data sets against each other. And the two things are closely related. Coefficient of variation is just the standard deviation divided by the mean of the values. So in this case, the standard deviation here would be 0.1. Okay. we've kind of rebranded coefficient of deviation, or coefficient of variation rather, and come up with a name, erosion variability index. I think putting the word erosion variability in there helps describe better what we're actually trying to measure, rather than coefficient of variation. It's a bit of an abstract term. So erosion variability index is what we will refer to it from now on, but it is numerically equal to coefficient of variation. So the standard deviation in the cluster eroded area divided by the mean of the cluster eroded area. So if you want to see that whole equation for that whole process from the beginning of calculating EVI, and everything else I'm going to show you from this point on will be EVI. So we calculate the eroded area per perforation, beginning with our images, and then simply sum those up to get the eroded area per cluster, calculate the mean of those cluster eroded areas, and then make our standard deviation calculation. Any bit of statistical numerical software, Excel is what I prefer to use, will make this calculation easily for you. And then finally, we divide that standard deviation by our mean to get our EVI number. Okay, let's try and dig into this EVI number and understand it a little more. So here's what we're really aiming for: no variation in the amount of propant per cluster. That infers equal fracture geometry, and that would give us an EVI value of 0. So EVI of 0 is our target, and if we start introducing some variability in there, we start seeing our EVI number increase. So I've put some examples in here, going all the way up to 0.7 on this page. I should say there's only one way to get an EVI of 0, and that's for every cluster to have exactly the same value. You can get an EVI of 0.1 or any of the other values you choose in various ways. These values can change, and yet you can still get a value of 0.1. So these are just examples, just really to try and show you the degree of variability that relates to, say, an EVI value of 0.6. And by the time we're getting up to 0.6 and 0.7, there's really quite a lot of variation going on here. We've got some overstimulated zones, and we've got some understimulated zones, given that we were trying to stimulate each of them, or have an eroded area of 0.2 square inches here. And this process continues. It doesn't stop at 0.7. We can go all the way on until we have the maximum value is reached when one cluster has all the eroded area, or if you like, one cluster has taken all the propants, or possibly all the fluid, and nothing else in the others. And that's where we reach our maximum. When it's a 6 cluster stage, that EVI value is 2.24 as seen there. If it was a 10 cluster stage, the EVI value would be higher. If it was a 4 cluster stage, it would be lower. It depends. That's how the maths work out. Depends on the number of clusters in the stage, what this ultimate value is. And of course, this is a value you never want to be going anywhere close to.